Okay, so today for research at TTIC, we have Zhiyuan Li, second-year faculty member here, and he's going to talk about long thoughts with short memory. So.
Thanks. So today I would like to talk about of my recent work on language model reasoning. Title is Pencil Long Thoughts with Short Memory. So first, this is a joint work with another 3 TTIC folks, including Chen Xiao with my first year students here, and Artie and David. So I would like to invite you to think about the following question at the beginning of the talk. When is pencil better than pen?
Works in space.
Excellent.
You can erase.
Yes. Excellent. So, right, the first answer is exactly this thing I learned from the movie 3 Idiots. And then they argue like there's another like space pen which somehow improves over pencil because of some other reasons which has got. But indeed, the second reason is something I'm going to focus today. Imagine you go to math exam without scratch paper. And for example, let's think about scenarios which are closer to our daily life example space. So something happens in this room in a month. In a month, you will have final intro of machine learning right here. And say you went to that exam without scratch paper. What are potential issues? Of course, I think that you will definitely provide that scratch paper. Let's just assume you don't have scratch paper. So you have to write on scratch on the final exam paper. So I've listed some issues. The first issue is that you can easily run out of scratch space. Because if you don't have a pen, you can erase. Very likely to end up a situation where you realize you have fantastic proof, but there's not enough room to write down a proof. That's the first type of issue because of space. And the second issue is that it also slows down your progress. Because when the exam paper is full of like old and obsolete tokens which are not necessarily useful for future computations, it will take you longer time to find the useful scratch out of the useless ones. And the third issue is that it also increases error rates. There are multiple reasons, just give simple ones. For example, you can copy the wrong number, which is from some wrong calculation. It could especially be possible if the time is limited, right? And you have to do things very fast and then error because you cannot erase the wrong answers.
So you can copy wrong number. The likelihood of doing that with the pen is higher because you have to turn pages. Is that?
Yeah. Right. And now I claim these are not only issues with pencil, but more generally, this is about whether we can erase and write, which is exactly what Greg said before. So we have lots of examples versus like non-erasable and erasable, except the pencil and pen we just mentioned. This contrast between erasable and non-erasable forms of writing is something we encounter frequently in real life. Another example here is the difference between CD-ROMs and USB flash drives. So even today, we still use both of them. Like we use CDs for installing drivers and playing like music in cars, and USB drives. USB flash drives for daily use like data transfer and storage. So by observing their usage, it is clear that non-erasable forms of writing offer higher data stability, meaning that the information is less prone to tampering or like accidental modification. Since also there's no need to consider like future edits, non-erasable writing also provides better durability over time. On the other hand, erasable writing is kind of like more space efficient and well suited for like drafting or scratching. But it's not like that appropriate for like a final official document. Like for example, you would not consider using a pencil to sign a legal document, right? So today's focus is another method about non-erasable writing, which people use daily. It is chain of thought by language model. And however, as we will see soon, by the nature of chain of thought, which is sort of like Scratch, it is not clear why it should be non-erasable. And indeed, so far, we don't really have an erasable counterpart yet. So just to make sure we are on the same page, we are going to discuss and define chain of thought a little bit. So in this talk, I will use chain of thought to refer to autoregressive next token generation. So this is different from the original meaning of chain of thought, which is original referred to a prompting technique, meaning if we ask language model to answer questions, provide similar question and answer templates where answer has the intermediate steps. And the original chain of thought prompting refers to provide such kind of like templates before the true question you want to ask. And this also improves the few-shot language model reasonability. And it is well known that generating intermediate steps before the final answer improves the reasoning capability of language model. We have both theoretical and empirical evidence. And to be more specifically and mathematically, this autoregressive next token generation is roughly the following process. You have like transformer architecture, which is consists of a sequence of a stack of decoder blocks. And each time you generate one token by doing a forward pass, and you take the token generated in the last position, and you concatenate and append it into the current input sequence, and you repeat until you generated some special token, which is end of sentence or end of article, and then you stop. Right, that's the definition of chain of thought. So probably most already knows like news about DeepSeek, and we have some difference up in the progress about chain of thought in 2025, which is this so-called long chain of thought. So we have a few models that exhibit this long chain of thought behavior, like OpenAI 01, 03, and DeepSeek R1, and K1.5. And I guess the common property here is that, this is from the DeepSeek R1 tech report, if you use reinforcement learning with outcome reward to train the model, then it will encourage the model to generate a longer COT, and as a result, it greatly improves reasoning capability.
So maybe we're going to address it, and feel free to also comment. But so we saw a talk, I guess this week, which reported pretty extensive results showing that chain of thought in general does not improve anything other than formal reasoning. Is that something you agree with? Should we think about that?
I don't agree, because formal reasoning, I mean, do you agree like DeepSeek, like say OpenAI 01, 03 mini high is better than 04, 40? I mean, 03 cannot do formal reasoning, right? Just solving math problem in natural languages.
No. So I think what Greg was saying is that anything that can be reasonably easily framed as a formal, either formal logic or mathematical problem, is improved a lot by chain of thought, but other things are not.
Right, I guess I agree. I mean, in that sense, formal means you have a reliable verifier which can decide if the outcome is good or not. And this is exactly what is required here. You need the outcome reward. If you don't have that, sure, it doesn't work.
And it doesn't work because we failed to teach it the right way to do chain of thought?
I think so.
I see.
Like when it's about moral judgments, I think even people disagree.
No, but like summarization, it doesn't produce adequate summarization. That's improve. Okay, we can.
Okay, yeah. But I guess here, like in this talk, maybe we are, at least I'm more focusing on this scenario where you do have this formal verifier, you can evaluate how good it is. And in particular, there's such a concept called aha moment, which can be seen from the context generated by like this. For example, this is an example from DeepSeek R1 tech report paper. When you use reinforcement learning to train the language model based on outcome, language model sometimes realize it's wrong, and or like sometimes it's realize like you should do something different and go back and do some other thing, and some like line in red, which is wait, there's a aha moment I can flag here, kind of like suggests a different thing, which is happened in this long chain of thought compared to the previous standard chain of thought, which just get from like kind of pre-training or this kind of super fine tuning. Question?
Sorry, this is going back a couple of slides, but you're kind of redefining chain of thought as just any autoregressive generation, right?
Yes, kind of.
Can you say a few more words about why?
Right. So
But yet, let me say a few words. But then it also sounds like you are thinking about problems that are what we usually do use traditional chain of thought for.
Alright.
So yeah, it feels a little contradictory. Can you say just a few more words?
yeah,
on
I
that?
guess when people say long chain of thought, this chain of thought is no longer like chain of thought prompting, just like you generate a long sequence of intermediate steps before then answering that final question. It's kind of like the community, they are changing the meaning of the word slightly over time, gradually. It's not my decision, but I thought that somehow I want to just. I feel like people are nowadays using, when they say long chain of thought, it's no longer referring to prompting technique.
So is it correct to say that you're thinking about settings where you're generating a bunch of tokens before you generate the target answer?
Kinds of. You're thinking about how you use R1 or like O1. Like you have first this, like in O1, previously you have hidden this thought process and they which is a bit sandwiched between two sync tokens, and in the end they summarize what happens in sync token. This kind of thing we are thinking about here.
Okay. I guess I would feel comfortable just calling that chain of thought. Because you have tokens that you don't really care about, that don't have to do with the answer, right? And then the final answer. Is that
right?
Okay.
Kind of.
Thanks.
Yeah, but now this O1 after DeepSeek R1, O3 is also given the entire thinking a sequence of tokens between two thinking tokens.
But the tokens you do not care about are still machine generated.
Sure. But if the prompt was summarize this document for me and the output was just the summary, that none of that would be chain of thought.
Yes.
It would still be autoregressive
From the
generation,
definition.
but it would not be chain of thought.
Right. That's. I should make that clarification a pattern earlier. Yeah.
Thanks.
So next I would like to argue. I would like to argue that this very long chain of thought actually cause some issue, and this is something we probably want to fix by making it erasable. Like thinking about doing planning with language model, what you want is just think about some examples. Like for example, you want to do course scheduling for TTIC. Each professor has this contact time, and also you have conflicts from classroom and things like different departments. And also think about scheduling prospective PhD student campus-based meeting, right? So we have reading groups on Friday, and each student can meet only one professor at the same time. Each professor can only meet one student at the same time. So they all kind of boil down to solving sort of satisfiability problem. You can return these as discrete variables. In the extreme case, it's written as 0-1 Boolean variables, and you have a bunch of constraints. And for such problems, the answer can typically be short, but there's this exponential time hypothesis which says that even 3 sets with n variables cannot be solved using less than exponential n time. So even the answer can be short, but you still is quite a lot of time to compute the answer. And in the case of COT and long COT, that means in worst case, you need exponentially long COT to allow the language model to compute this. And even though, in a very trivial way, if you just enumerate all these possible assignments from x1 to xn and check them if they verify, it takes O(n) space. But COT, if you want COT with language model with COT to solve it, it will take exponential space. That's kind of how things can become problematic here. And we can summarize in a higher level, still from 3 perspectives. The first is space. COT length can go beyond GPU memory. So this is a kind of hardware restriction. For example, when we do this autoregressive generation, memory needs to store the previous KV cache, which is the embedding size times the sequence length times the number of layers. And that's just some concrete calculation for lemma 3.1, which takes single sentence of 120K length. And the 405 billion lemmas 3.1 model requires 123 gigabytes to just store the KV cache. This cannot be done on a single GPU, even if you have an H100. And this restriction on GPU memory also brings effects in time and accuracy. It makes inference slower, even the length is not that long and it fits in GPU memory. Because the time to spend on next token when length becomes very long is basically proportional to the sequence length. And the time when it's kind of like a vague concept here. It should be more specific when you can think from multiple perspectives, like one is flops, which is like a floating point operations per second. It's total floating point operations, and the other thing is this I/O complexity, right? Like how many data you need to load into your L1, L2, L3 cache from your GPU memory, and that's often the real bottleneck for improving reasoning, like inference throughput for these mainstream models. And third issue is it could lead to worse performance. And there are various challenges for long context, just name a few. Like for example, you probably need higher precision, like for attention. And also you may have the issue of attention dilution because the hard attention, which is hard for short context, might not be hard enough for longer context. The attention might be diluted. So let's go back to this table. What I'm trying to say so far is that for a bunch of type of problems, a chain of thought which is used as Scratch, it doesn't really need to be non-erasable. We don't really need to have higher guessability and better durability. And it would be more natural and more useful to make it actually erasable. And this is what this talk is about. We're going to introduce a reduction rule to make chain of thought erasable. So we call our method pencil. It is the first lectures of context dependent inference and learning. So it's recursive, it erases. So the key idea, or the central part is very simple. We just add 3 tokens, special tokens to the vocabulary. They are call, step, and return. So this is kind of motivated by this idea of using stacks in programming language and the function calls. Right, when you call a function, you only get to you only save the final return value, and the intermediate calculations are temporary, and the local is just you lose that after you get the return value from function. It's kind of thing you want to get here. So basically, pencil method means you apply the volume reduction rule whenever possible during the chain of thought generation. So here, C, T, A, there are 3 strings. They're strings of tokens. You can think C is like context, and T is like some thought, which you don't need in the future, and A is answer. And this might be a little bit vague because the parsing might not be unique. So what I really mean here is that you have some additional restriction on A and T. You cannot have step token in A, and you cannot have call token in T. In other words, the reduction rule means the following program. Whenever language model generates a return token, you find the most recent step token. Okay? And then you find the most recent call token before the step token. And you finish your parsing. And then if all these 2 tokens exist, the matching happens and the reduction will be triggered. The source string between call and step goes away, along with other special tokens, 3 special tokens. Does this make sense to everyone?
So just to clarify, if you have multiple things following by multiple steps, you can only erase the most recent one.
Most recent. Yeah. So the program is very well defined, right?
Counterintuitive though, because wouldn't you often want to erase oldest things because they're less relevant?
Think about calling function. You can call function recursively, right? So you do have this.
No, I understand that. Right, makes sense here. Okay.
Question, please.
You can think of the context as analogous to a stack, copying a stack frame. there can be many calls occurring in that context that you haven't returned from.
Sorts forms the stack.
So this is eliminate, this is returning from a stack frame, this rewrite rule. But there can be many, but that C can be a whole stack that you haven't yet.
Return is a pop.
Yes. So pop can be done deep, in a deeply nested stack.
It's a stack.
Does this mean the inside the chain of thought you cannot have inside T you cannot have another, so that there cannot be nested chain of thought?
No, this doesn't. It's completely possible, right? Because this T is just some string, and it can be the remaining of a previous reduction output of reduction rule. This is completely possible.
So if you enter some, so before you reach in the final A and return, if during T you want to do some small scaled
Yeah.
CTA
Yeah.
inside that,
Yeah.
that's
You're going to apply this reduction rule multiple times during the generation process.
so why you say T does not have T cannot have any call?
Right. So if T has another call, then I will just take the segment between T before the last call. After the last call, the new T, right?
Yeah.
That would what happens.
So, am I interpreting correctly? You can call a subroutine. That subroutine has to return before you return. You can't call a subroutine and then you return and then the subroutine returns. So T will have already done that by the time you get to this.
So nesting is allowed, but some kind of not fully nesting, but
Okay, so technically what is allowed is just the following detection program. When you detect the return, find the most recent step, and then you find the most recent call before step. And then if all these step and call exist, then you trigger the reduction. This is very way to find.
so you cannot initiate another chain of thought, and if you want to return outside, then that's not allowed. But it's not not intuitive anyway. So
So you can generate many calls in a row without returning from any of them. But then when you return, you'll only return from the most recent call you made.
You can't go further deficit erase it. It's on generation.
So next we were talk about like how to sync with pencil. So this is the reduction rule, and trying to give more some intuition about these letters, like these strings. So C means context, which embeds the upcoming subproblems to be solved. For example, C should like include the information about function to be invoked. And T means thought, like it's intermediate steps towards solving the subproblem. And this is only useful towards getting the answer of the subproblem, but not useful for future reasoning. And A is the answer, which is answer of the subproblem, and this is useful for future reasoning, and we want to keep it. That's kind of like a high-level idea between CTA. So I want to walk you through a concrete example with pencil for this QBF exam, which is quantified Boolean formula. So this is kind of like a except it's kind of like special case of QBF. So in general form, you can have this both existing and for all operate like quantifiers in this formula, and in the end you have some this predicate. So what we know is that QBF is p-space complete, and it means this is the hardest problem solvable using unlimited time and space polynomial to implements. So next, I want to walk you through a concrete example. So here we have a prompt, which is a problem. This is a QBF with 2 variables in 6 clauses. It asks, does there exist, so first, all these variables are Boolean variables. So it asks, does there exist x2 from 0, 1, such that for all x1 from 0, 1, all these 6 clauses are true.
What is the meaning of the first class? If you take or of something, it's literal, it will always be one, right? Oh, the first class, two or not two is always one.
Yes, yes.
Or it's on purpose. But just here.
Yeah. It's one. It's always one.
Okay, good.
It's fine.
It's randomly purpose, yeah.
You passed the intro to logic. So.
Let's see.
So next we're going to present something designed by humans, right? This is designed by us, not like automatically learned by language model using reinforcement learning. This somehow we're going to show how we can think with pencil, and then I will show how we can teach transformer to think with pencil. But for now, let's just see how human can think with pencil with space efficiency. So basically, what I'm going to maybe I'm going to draw a tree. So basically, this problem is like you have exist x2, and the two branch are true, false, and you have this is for or x1, and you another get two branch which are true, false. And what we are doing here, just recursively going down the tree, and first ask if the outcome of value of this subtree is true or false. If we know both value of this tree and this subtree, then we can just using one step to get the answer of the final question. And then to know this, we have to facing another two branches which are true and false for x1, and that's what we are doing. We're going to generate, and here you go into some leaf node where you can actually evaluate the truthfulness of the predicate, and when that happens, it returns. So here, I'm not going to generate like the generation of each token. I'm going to present the generation of a sequence of tokens until a return happens. So here's the font in bold, the text in bold. They are like generated in this step, and the text in blue, that the text that's going to be erased after the reduction rule is going to be applied. Okay. So here what happens is really you go down the first branch, true, and here you check, it's like false, okay, false. Then you return. And now you go step 2. In step 2, you see that sorry, I think here we actually first tried this branch first, which is both false, and then in step 2 we try this branch, which is true, and then we return, and we got this here. This is false. And we keep doing this until we traverse the entire tree, and we got the final answer, which is false. So does this make sense? So this is doable because we can like manually write the code like to iteratively, recursively generating this. This is not generated by language model yet. Okay. Sure. Of course we have a question like, can this like transformer learn how to use pencil in the following way, right? It's not obvious that transformer can learn this by just optimizing using Adam on some training data set, but we will share this in experiments.
So I have a suspicion, and maybe tell me if it's false, that this is a little bit of a, it's particularly true that you can do this for Boolean logic satisfaction problems, because basically you're just looking for one thing, let's say you have exists, the moment you find it, you are done, right? Or for all, the moment you find something which doesn't satisfy, you're done. And so you just need to kind of go through the process.
Yeah. So
that's have a clear frontier. But if you're solving, let's say, arithmetic, is that still true?
So next I'm going to answer this question. Okay. So we're going to show the pencil allows you to do universal space simplification. Okay. So we just see that pencil can solve QBF with linear space. And how about other problems? So let's just work out. Is it universal? Do we need more complicated reduction rules to make universal things happen? The answer is yes, it is universal. The way we show this is that we're going to prove the following theorem, which says that for every Turing machine, there's a transformer such that for our input sequence, pencil with this transformer can simulate the Turing machine. And the total number of tokens generated with pencil is upper bounded by the runtime of Turing machine times some constant. And the maximum context length used by pencil is upper bounded by some constant times the total space used by Turing machine. So they exactly matches. And here I have an asterisk here. The transformer means like it's a finite size. It does size does not depend on the input sequence length, and it also has finite parameter precision. But we do need to assume infinite precision in the forward path to avoid all this painful discussion on finite precision truncation, which I don't know how to make them like perfectly correct. So, and we also need to assume you have like average hard attention, which is like kind of like typically assumed in previous works.
What does it mean, average hard?
Yeah. So softmax attention has some notion called temperature, right? And when you take temperature to 0 for each instance, you got average hard attention. You basically get a uniform distribution over all the argmax. So you can kind of like simulate that if you can have like very large number in your transformer, you make the temperature super high, and you get hard average attention.
It just means no attention, in fact. Okay. That just means
No, it's uniform over the argmax.
Over argmax.
So it's dropping everything but the actual optimizer. And all he's pointing out is that the actual optimizers might tie.
So this is instance-wise limit of usual attention when taking beta temperature to 0. So this is our theoretical results. Like, by this, it kind of like suggests that pencil can do universal computation, space-efficient computation with transformer. If the transformer has certain enough high precision. And we also have to compare this to previous works on showing attention and Turing complete. For example, there's a theorem by Maria et al. In 2024. It basically has the same set of assumptions as we have on transformers, except they claim finite precision, but the things are a bit tricky there. They show that COT, standard COT, can simulate a Turing machine with total number of tokens generated equal to the runtime of Turing machine. However, that also means, because in standard COT, the total number of tokens generated roughly is just the same as maximum context length if you ignore the input length. It means the maximum context length is also the runtime of the Turing machine. So that's the gap here. And the gap can be in particular large when you're talking about problems like satisfiability and QBF. There will be a Pauli and exponential gap between space and time. And here we don't really care about that the log space that much, because anyway, your input length is already linear in itself. So we care more about Pauli-verse expansion instead of like log versus Pauli. So I have to say this idea of like simulating, like showing attention and Turing complete is not first does not first occur in Maria 2024. Like actually, this idea have been introduced in previous works by Paris et al. In 2021. I think they have actually another paper in 2019, but somehow the final paper is accepted by JMR in 2021, and the title of the paper is Attention and Turing Complete. And there's also another paper by Colin Wei and Chen Yuma and other co-author, I forgot her name, and they show that transformer can statistically meaningfully approximate Turing machine. Okay, so next I want to spend 2 slides to quickly go through the high-level idea of the improvement, why we can make transformer space efficient, pencil space efficient, which means using exact maximum context length as the memory that Turing machine is going to use. Just a bit notations. The Turing machine, we have Q which is state space, and A is alphabet, and B is blank token, and then we have a transition function delta. These are standard notations. And the new notation I'm going to introduce is autoregressive machine. I feel like this is implicit in literature, but I just want to formalize it a bit, then give it a name. Then you have some vocabulary, and you have an next token generator, which maps a sequence of tokens to one token, just as the most language model does. And you can append this token to your input token and go to new string, and then you can recursively apply this function with longer string until you get some stopping signal, which is seeing some end of sentence token. And Chen Xiao has made this very nice picture showing how do you simulate Turing machine with autoregressive machine. The idea is that you're going to let autoregressive machine at each step output the transition of Turing machine is going to make at that step. Okay? So this is almost a trivial simulation, but then let me just walk through this. So initially, Turing machine has 2 tokens on tape, and all these B's, they are like blank tokens. You have many of them, and that's the only token which can occur infinitely often during this whole execution of Turing machine process. Now we have 2 steps here. So the first step, what Turing machine does is that it reads blank token and at state 0 and decides to transition to another state Q1 and rewrites the old token as 1 and move towards right. And what the autoregressive machine does is it's going to put a new token which just exactly record what the Turing machine is going to do in this step. And same thing happens for step 2. And now I claim information theoretically, it is possible to just simulate this Turing machine with this fast sequence generated by this autoregressive machine, because it encodes every information about the complete running trace of the Turing machine, right? Though it's like a bit redundant, because Turing machine can write and rewrite and rewrite and rewrite. You only keep the last token, but the autoregressive machine keeps everything. But transformer can just do the job of this autoregressive machine. This is the main idea behind transformer with COT Turing complete. This is first introduced by Press AO in 2021. So the only technical thing here is just to show that there is a transformer, which given the running trace of Turing machine up to time t as input, it can generate the next token, next transition the Turing machine is going to do. Just need to show there is a transformer that does that. For every Turing machine, there is a transformer that does that. And this is not very difficult if you assume transformer has enough precision and right activation function in NLP. We're not going to the detail of that. So these slides are just summarizing previous works. So the key observation for simulating Turing machine with pencil in a space-efficient way is, as I just said, this running trace of Turing machine is much longer than the actual configuration of Turing machine. The configuration of Turing machine contains content on tape, its state, and its current head position. This is where the gap comes from. And I'm going to introduce a special way to use pencil reduction rule to allow us to do something more efficient, which is this. I set C to be empty string and remove C. I always ensure that the starting token of my string is call, and I set A, which is answer, to have the following format. It is call followed by another T prime, which is another string. And basically, the reduction becomes something like this. It allows you to do this summarize mechanism. So when you have some T, and you want to summarize to something equivalent for future computation purpose, but it's shorter, since this is T prime. And what you can do is just generate step and a call, and then write down the T prime, and write another return. In our reduction rule, we'll basically just replace this by call T prime. this is a particular way to use pencil, which allows you to do summarize. Question?
So is it clear how you find? So you have to figure out what T prime should be. So I guess
Yeah, you should.
you do that by kind of going back
Yeah,
and saying
so-
what would the state look like.
So if I'm going to write the summary, I can of course understand what should I do, right? If you have long trace of Turing machine, I can just condense into a sequence which is as long as the memory of Turing machine, right? Just move right and write something on tape, move right and write something on tape until you go to end of tape. If you move your hand back. So that thing exists. And the transformer can do it, but I'm not going to the detail of like constructing transformer doing that. That's kind of like more technical. But it just cannot exist.
So this is a subroutine, basically.
Cancel. Yeah. Right. So the ideal way to summarize is that basically, so here the T is basically a bunch of running traces of Turing machine, and when you summarize, you want to summarize to the kind of like the shortest equivalent trace of Turing machine, but gets the same configuration. The question here is how when should we summarize? Right, you have a few choices. Next, I'm going to use time to represent runtime Turing machine and space for the space used by Turing machine. You have a few choices. The first choice is you never summarize. If you never summarize, then the total number of tokens generated is just a time. And the drawback is max context length is also time. And another obvious naive choice is summarize every step. So this ensures the maximum context length is just the space. But that means the total number of tokens generated by autoregressive machine is time space. Because now each summarize you have to rewrite the entire configuration of Turing machine. So the reasonable thing to do here is you only summarize when you can gain a lot from summarization. Means you only summarize when you realize if you can halve the sequence length by summarization. Okay, it's kind of like an adaptive thing, and this transformer can do this comparison. It's not difficult. But if you do this, you will realize first you trivially get the upper bound for maximum context length, because if your current length of T is going to be larger than twice the maximum sequence context length or twice the space of Turing machine, you definitely trigger this summary process. Because if it gets too long, you can definitely gain a lot by summarize it. And you can, in this way, you also avoid doing summary too often, and you don't waste most of your times, most of the tokens on just to copy what you have before. I'm not going to prove it, but just claim this is true. It's not difficult to prove. Okay, so this is the end of the theory part. Next, we are going to talk about experiments. So basically, summary of theory. Theory shows that pencil can do universal space efficient computation. But two questions remains. So the first question is can transformer learn how to use pencil? And the second question is, how does pencil compare to just a standard COT in terms of learnability? Is it more difficult to learn? And we don't have theory for this, and we want to answer this with experiments. And we evaluate this, we try to investigate into these questions with 3 tasks, which are reset, QBF, and Einstein puzzle. So I have talked about already reset and QBF. I will talk about Einstein puzzle in one slide. So basically for each task, we design an algorithm which uses pencil to generate the training test set for the language model to learn. And we are also, from that gets the COT counterpart, which is just the sequence of all the tokens generated by the language model using pencil, actually generated by us using pencil. And we can concatenate them without any reduction rule, and it becomes a COT counterpart. So this is a concrete example. We go back to QBF. On the right is a full generation and reduction process with pencil. And in this process, pencil generates a bunch of tokens, and we just concatenate all those tokens into a single sequence, you get COT. And you can train transformer on that, and transformer can learn it. Okay? So that's an empirical observation. But it's probably not hard to prove the transformer can do it. So that's our definition for COT counterpart. Does that make sense? Any question?
So just to make sure I understand, okay, so you have some examples of these tasks for which you have the ground truth and ground truth chain of thought. That's the box on the left, right?
On the left, yes.
And you have some examples of that, and you basically train the transformer to produce that.
Yeah, like standard instruction flow and next token prediction.
Wait, you train it to produce the chain of thought?
Well, you give some examples of the full chain of thought
Yeah.
with pencil tokens.
Yeah.
And where do those come from? From they're manually constructed?
Yeah, train to write some program to generate those.
Program. No, but the program knows about return, sep, and call tokens?
Yes, we designed this.
Oh, you have a program? I
Yeah,
see.
we have program. We have program, and we want transformer to learn how to use this from imitating our program.
I got it.
We're not
Okay.
doing reinforcement learning here. That's
And-
not the idea thing.
And are you going to tell us like how many of such examples you need?
Yes, I'm going to show some demo experiments. So this is the definition of COT. And next, I'm going to also give you an example of instant puzzle. So instant puzzle, basically something looks like this. You have the prompt. This is the problem. And this is like what the solution like. So it's not clear if this puzzle has anything to do with Albert Einstein, but it's it's a name maybe indicating this puzzle, solving this puzzle requires some intelligence.
Maybe it's Einstein bagels.
No, right? No. But so this is a 3x3 case. It's really trivial. It's really simple. But if you in standard one is like 5x5, you can just search it easily and try to solve. It's quite simple. It takes me a few minutes to solve that. But in this case, we have like a 3x3 puzzle. Basically, you can think it as a special type of satisfiability problem, but this is in natural language. And for size n Einstein puzzle, the solution space is essentially this n by n table, and each entry has value ranging from like 1 to n. So each entry here has n possibilities. So the solution space is n cubed n squared.
So I realize it's completely tangential, but nothing in the prompt mentions fish. Why should anyone own a fish?
That's why you need to be Einstein.
Sorry.
Right, owns the fish.
You can only have one pet.
Yeah. So the implicit assumption here is that right. I'm going to get that. So except these explicit constraints, you also have implicit uniqueness constraints. So everyone only owns one thing, and everything and every house is only owned by one person.
So, sorry, maybe it's not very important, but is it possible to actually write this explicitly as a SAT problem?
Yeah, it's very simple.
Yes.
It's very simple.
Okay.
But
It will be very efficient working on it.
I see.
But currently it is in the form of natural language. But you can do it as set. Okay, so this is puzzle. So I'm not going to tell you like what are the solutions we create for solving these problems, but I'm just going to present the difference between the length, maximum sequence length, if you solve it with pencil and versus the entire COT. So the basic takeaway message here is that when the problem size increases, the gap between pencil and COT kind of like increases like exponentially. So for pencil, it's kind of like more like polynomial, and for COT, is like exponential.
But should we be comparing like the best we can do with pencil and the best we can do with COT? Like here, kind of like you made the algorithm work for the pencil, and then you're trying to force COT to learn the same thing.
Right. The issue is that we don't know what's the best algorithm for 3 stats. Sorry. Right. We don't have this in T, right?
Yeah, but like you should really be comparing like this thing with pencil with like the best you can do with COT and some
I
other
see.
training. Yeah.
Right. So we don't have that yet. Sorry about that. But this is like I mean here like it's for another purpose kind of like fair because the language model is just going to learn to predict the same set of tokens. but they are going to predict the same set of tokens with different prefix. It's kind of like makes things a little bit easier to compare for other purposes we will see later. So, okay, I'm going to talk about the training objective. How do we train it? So we have like a ground truth we have data distribution P star, and Y is the design COT. And P theta is like probability of the language model given through the theta. And our training objective for COT is just a standard one, the next token prediction loss. And the training objective for Pencil is a little bit different. You're going to predict the next token in COT, not based on the entire prefix in COT, but you're going to based on what you are going to have in Pencil. So something from the COT are going to be deleted. And this is captured by this function phi. Phi is equivalent to iteratively applying the reduction rule of Pencil on this string until it converges. This is, in other words, like phi xy is the remaining string after language model consecutively generate like y1, y2 to y minus 1, which is the last token in Pencil.
Convergence means no change?
No change. Right, because each time you apply the reduction rule, the sequence length is going to be strictly decreasing. So after finally in terms of application of reduction rule, it converges.
Not sure I understand. So you're comparing COT versus kind of Pencil, but both of them are trained on the output of this program that you previously mentioned, which kind of generates these tokens.
Yes.
Isn't it like kind of evaluating an algorithms class when the only algorithm you taught your students was brute force search? It's
Good idea.
Good idea. So I think it's not completely brute force search. For space data, there's something like better than brute force search, like unit propagation. And we actually do DPL algorithm. But honestly, I don't know. I mean, we don't implement a much better algorithm for QBF than brute force search.
okay, but yeah, I guess for these problems, maybe.
Yeah, maybe you can improve the exponents, but we're not doing that here. So, and basically what we know is that phi x y is shorter than xy. So this means the prefix becomes shorter, and actually this makes Pencil training needs fewer flops per step. And this also applies to inference. Right? Because shorter prefix makes like less compute needs needed attention. So let's see some actual experiments. So here we have like full context length. Basically means like we're not going to set a maximum context length for the transformer, just going to take whatever the training data look like. So in this case, we are presenting the train curve in terms of loss, accuracy, and trace rate. Trace rate means the average rate over every token in the train data in COT, and accuracy only concerns about final answer. And we're plotting them against the number of iterations. So here we basically see that in terms of accuracy, they're close, but in terms of training loss, Pencil actually make training loss decrease faster. And next, we're going to compare them in terms of flops. So here, flops we are already. It's not the exact flops. We're mainly focusing on the flops from the attention, which scales, which becomes a major part when context length becomes very long. We're using a very small model here, which is like 20 million. The embedding size is very small, but the sequence size is very long. So it's different from the standard scaling law setting, where your embedding size is comparable to the sequence length, but here with sequence length is much longer, so the most of flops actually comes from attention. And because Pencil uses less flops per step, so it's actually much faster than COT in terms of training flops. And this is observation here. And we also try to scale up this problem size to 10, and in which case the context length becomes too long, and we cannot just like put them in GPU, and we have to set like a maximum context length for transformer, which is 2000. So with this like restriction of maximum context length, Pencil becomes much better than COT as long as the like COT is long and the standard like COT transformer trained with standard COT are not able to learn the entire COT and put them into the sequence length, and they immediately leads to like a drop in test accuracy for both 3-set and QBF. Okay, so this is the last experimental question.
Accuracies are usually not monotonic in size. Is that just a randomness effect or something you see? As you increase the size of the problem?
Yeah, there could be some randomness, I guess, but if you look at the trace rate, which has like larger samples, it's kind of like become monotone. Trace rate means like a average accuracy over every token you predict, and this probably might be due to the issue of like our evaluation data set is not so large because evaluation is quite expensive because you have to do a very long iterative inference. So that's kind of expensive here. I think that's due to variance maybe. This is the last experiment we're going to show. It's about Einstein puzzle. So here we have a maximum, similarly we have a maximum context length of 2048, and we show that pencil can even get 97% accuracy for 5x5 Einstein puzzle, but COT, standard COT gets like only 25% accuracy. And we also compare like their performance on 3x3 Einstein puzzle on the right for different model size and different context lengths. And pencil like consistently beat COT by a large margin, except when the model becomes extremely statistical. So the observation here, to summarize, is pencil achieves better test accuracy than COT, even with less parameter count and less context length, or even for more difficult tasks. Okay, so at the beginning talk, we talked about like issues of COT, and I would like to summarize it with like benefits of pencil. The first thing is about space still. It reduces context length. It reduces the context length from the time complexity of the problem to the space complexity of the problem in the ideal scenario. And it can make training and inference faster even without hitting the context length limit, because time spent on generation X token is proportional to sequence length before it, and also leads to better test accuracy. So next, I would like to conclude. So in this talk, we propose pencil, which is autoregressive generation plus a reduction rule to reduce the maximum context length of language model reasoning. And it allows universal efficient computation by simulating Turing machine with same amount of time and space. And this improvement in context length also implies more efficient training and inference in terms like flops and I/O capacity. And we get an impressive accuracy on Einstein puzzle with a very small 25 million model and 2000 context length. And in contrast, like, okay, I can also mention the time, which is like for the inference, which is like 43 seconds in average. In contrast, I can tell about like this test of 5x5 Einstein model on OpenAI models, but 4 cannot solve it. 4 gives the answer in 30 seconds, writing a program for search and generates the answer. And O1 can solve it with like 80 minutes, and O3 mini high can also solve it with 2 minutes. But here we are not doing any optimization for inference. We're not even using KB cache. So our 43 seconds is actually get using nano GPT code based by Andrew capacity, where each time you generate an X token, you're doing a full computation for the pass. So in principle, this could be optimized in a significant way. So maybe I'm running out of time, but I guess briefly go through some ongoing follow-up works. Thinking about simulating RAM instead of between machine and pencil. And currently we're generating data in a case-by-case way. We want to have an interpreter automatically convert trace of Python code to pencil trained data. And something David is working on. You can get universal prompting. Basically, you get a universal Python program, which is a Python interpreter, which you take the Python program, the code as input, and you generate the answer. And I'm also interested in have a pure function core variant of pencil, instead of like one transformer, I'm going to have a stack of transformers. Each time I'm just going to like have special tokens to let the transformer to ask a question, and this question will be pushed into the next level of stack, and the new transformer will answer it. And this also gives me an opportunity to answer this question by some external expert, maybe like GPT-01. But it doesn't have to be the same model to answer it. I can like outsource this question. Hope is I have better learnability and maybe even better generalization behavior, because I'm in this case of 3 sets, I'm reducing problems of larger size n to smaller size. And some future directions I'm not really working on now, but I'm interested in is, first thing is better implementation of training on this tree structured input as opposed to like just input sequence. Because when you have pencil, like you have a lot of branches, like you don't have input sequence really, you have the input tree. And in principle, you can see the flops are small, but I don't really have a very good, easy way to fit this into the current GPU architecture. But in theory, it's trivial. The problem here is that multiple subsequences, they share the same prefix, so you shouldn't compute the KV cache in the forward pass multiple times. You just share these KV values in the forward pass. So the other thing which is very exciting is, can we teach DeepSeek R1 to use pencil? Maybe some instruction tuning and another round of outcome reward-based reinforcement learning. And maybe you want to plus some like lens punishment. So it motivates DeepSeek R1 to use pencil to reduce the lens. And also a follow-up question is, how do we get instruction data with pencil? But if you want to use instruction to R1. So we should not try to label them ourselves or like hire people to label it. I feel like that's very expensive. But maybe I'm thinking about like getting some automatic way, for example, turning like search tree in Ling into pencil with any data. And or in general, like turning some running trees of Python into pencil. Whenever they have this like recursive like stack behavior, it can be useful. Okay, that's the end of the question. That's the end of the
We're a little over time, but maybe one quick question.
So it's like kind of like memoization, right, for transformers. I have a question. Sometimes thought process is important. Sometimes, like imagine a Fibonacci. When you're solving the Fibonacci, you have to think a bit, like recursively find upper bounds and sum them together, like some function like that, where in the thinking process is important, and you want to remember the thinking process. If you discard the thinking process, you will lose a lot of information. So it goes back to the like, when do you like?
So there are two questions. The first question is like, give me the code of Fibonacci and ask, give me definition of Fibonacci sequence and ask what is the nth number of that. This question, the first question is to compute the nth number, give a definition. The second question is like, you give me a bunch of sequences and let me to guess what is the nth number of this sequence. Right? The sequence involves some kind of like a learning, right? So that thing would be useful to test a bunch of hypotheses. Basically, you want to run something like minimum interpolating solution, minimum complexity interpolating solution, which is
I guess the question is like a recursive thinking, like recursive instances of thinking, but the thinking is the same on each recursion. So you would want to remember how you solve the first instance and then recursively apply it to the next sequences that you see.
Wait, your question, do you know what the definition of Fibonacci sequence? Do you know that?
Yeah.
You know that? You don't want to remember, it's just a plus. What do you want to remember?
No. I'm just saying Fibonacci-like problem in terms of like it has a recursion. But I'm just saying like the reduction rule, like how do you know it's half this sequence? Like how do you decide that? Like that, I think the question.
Right. So I mean, currently we are designing it by ourselves, but the hope is we can link it with reinforcement learning, right? Like
so when to reduce?
Yeah. Let's think about like you're teaching a course. Like you have two blackboards, right? We'll like do a board talk and you use all the space on the board. And you kind of decide what you want to erase. You plan it ahead, right? And you have two boards used alternatively. How do you learn that, right? This is some kind of thing I want the transformer to learn.
I feel like that's the hard part.
So, additional questions. Zhiyuan will be here indefinitely. Yeah. So, additional questions.